Welcome to this presentation. I'm Caroline Pénicaud and I'm going to present you the environmental performance of new processes for the production of fructo and galacto oligosaccharides. Fructo and galacto oligosaccharides, FOS and GOS, are short-chain carbohydrates naturally present in plants. They promote the growth in the gut of bacteria with beneficial health properties. They are considered as prebiotics. However, their benefits go beyond their prebiotic properties as they are low-caloric sweeteners, give a feeling of satiety, contribute to body weight control, relieve constipation, have a low glycemic index, and are not cardiogenic. Therefore, FOS and GOS are increasingly used in the formulation of dairy products, beverage, bakery products, and some sweets, converting them in functional foods. As FOS and GOS can be incorporated into many products, their demand has greatly increased worldwide over time. In the framework of the European project Premium, FOS and GOS are used to increase preservation of lactic acid bacteria. Lactic acid bacteria are very useful to obtain fermented products, but technological operations to preserve them reduce their viability and, by consequence, their effectiveness. Generally, protective molecules such as disaccharides are used. However, oligosaccharides such as FOS and GOS have shown similar protective effects with complementary prebiotic benefits. From a technological point of view, these prebiotics can be produced by enzymatic synthesis using disaccharides or other substrates as raw materials, or by extraction and hydrolysis from different natural sources, mainly from roots and legume seeds. Thus, the obtention by valorization of biomass and their prebiotic properties give them an interesting added value. However, their use is currently limited due to the lack of control of their effectiveness in relation to their composition and the lack of knowledge of the interaction mechanisms to produce oligosaccharides at the right degree of polymerization. The objectives of the Premium project are to remove these scientific and technological limitations by taking into account the quality of the product from the laboratory to the industrial scale and by reducing the environmental footprint of the processes. To the best of our knowledge, no environmental study has been published with special focus on the environmental footprints of different production schemes of FOS and GOS. The aim of this study was thus to assess and compare by life cycle assessment the environmental performance of FOS and GOS productions by enzymatic synthesis or hydrolysis from different substrates: sucrose and lactose for enzymatic synthesis of FOS and GOS respectively, hydrolysis of yacon potato and chickpea seeds to obtain FOS and GOS respectively. We chose a cradle-to-gate approach to assess the enzymatic and hydrolysis scenario. So we considered the substrate preparation and extraction as well as the production of FOS and GOS, but we did not consider the final use and/or final disposal of FOS and GOS. Among the processes considered in the production life cycle, centrifugation, purification, freezing and freeze-drying were performed after the extraction phase. To allow comparisons between the systems under study, the functional unit was defined as 100 grams of FOS-GOS produced by enzymatic synthesis or hydrolysis. Inventory data of the foreground systems, such as electricity consumption, as well as use of chemicals, enzymes, or water, were average data at the laboratory scale. Background data were taken from the EcoInvent database. Environmental impacts were quantified with the environmental footprint method implemented in CIMAPRO software. The hotspots associated with enzymatic synthesis were the enzymatic synthesis itself and the purification stages, both for FOS and GOS productions, which presented similar environmental impacts. Enzymatic synthesis was responsible of about 60% of the impacts on all impact categories, while purification was responsible of about 20% of the impacts on all impact categories. The impact of enzymatic synthesis was mainly due to electricity requiring a reactor at 50 degrees during 24 hours and subsequently enzyme inactivation at 95 degrees. The impact of the purification was mainly due to the use of 1.5 kilograms of ethanol to obtain the final product rich on FOS or GOS and with low content of monosaccharides. The other steps required the lowest amount of electricity and no material inputs. Therefore, their contribution to the environmental profile was negligible regardless the impact category. The hotspots associated with the hydrolysis were related to the substrate extraction and the freeze drying, although we obtained differences in the relative values and categories. For FOS production, substrate extraction contributed to 39% and freeze drying to 26% of the impacts. For GOS production, substrate extraction contributed to 57% and freeze drying to 16% of the impacts. For both FOS and GOS productions, purification contributed to about 16% of the impacts. Freeze drying contribution was due to electricity consumption it required, and purification contribution was due to ethanol consumption, as for enzymatic synthesis. The contribution of the substrate extraction step was due to the production process of yacon potato and chickpeas together with solid waste generated after extraction of FOS and GOS from its raw materials. As for enzymatic synthesis, the contributions of the other process steps were negligible. A remarkable difference could be noticed between the environmental impacts of the two processes. Enzymatic synthesis caused significantly less environmental damages than hydrolysis for both FOS and GOS and on all impact categories, except for non-cancer human health effects and freshwater ecotoxicity, but the difference in these cases is very low. This should be directly related with differences on the production systems and the substrates used. Although the two processes share a number of stages in common, cleaning, centrifugation, storage, and purification, a significant difference between them was observed in the first stage, the enzymatic synthesis of FOS-GOS from sucrose lactose, or their extraction from biomass, yacon potato or chickpea. From the energy use point of view, the energy consumptions were comparable for both enzymatic synthesis and hydrolysis and could not explain the observed differences. Enzymatic synthesis implied an enzymatic step based on the use of a cocktail of enzymes with temperatures around 50 degrees during 24 hours of reaction and 95 degrees for enzyme inactivation. Hydrolysis included a hydrothermal process under non-isothermal conditions carried out at temperatures between 50 degrees and 100 degrees, but only for 2 hours, requiring rather low energy amount. However, hydrolysis process also involved the additional step of freeze drying during storage, increasing significantly the electricity requirements of the whole process. Finally, the differences between the environmental impacts were mainly due to the huge difference between the amounts of raw materials necessary for the two scenarios. about 500 grams of sucrose or lactose for enzymatic synthesis, and more than 5 kilograms of yacon potato or chickpea for hydrolysis. The interrelated consequence was the high amount of solid wastes generated in hydrolysis process, also causing an environmental load. Accordingly, hydrolysis reported the worst environmental results. Among the two hydrolysis processes, the production of FOS caused less impact than the production of GOS, except for water scarcity and mineral and metal use. Logically, it was due to the more important environmental impact associated to chickpea production than the environmental impact of yacon potato production. No literature data are available on these systems for comparison. However, such a study does not claim providing precise environmental impacts of the processes, especially because the study has been conducted at laboratory scale, which can be quite far away from an industrial process. Nevertheless, such an approach highlights areas of concern in further development of the processes and should be used iteratively at each development stage in order to check if environmental burdens have been decreased by new development and not transferred to another step of the system. Such an iterative approach could ensure eco-design of the production processes. The production of prebiotics like FOS and GOS is receiving special attention in the food industry due to their health benefits. In our study, we analyzed by life cycle assessment two different scenarios at laboratory scales for producing original mixtures of FOS and GOS. Hydrolysis process generated more environmental impacts than enzymatic synthesis. With regard to the production processes themselves, special attention must be paid on three specific stages: time of synthesis, freeze drying, and purification of the final product. The enzymatic-based synthesis involved the utilization of enzymes whose production and use require large times of incubation, meaning energy consumption. The hydrolytic production was carried out at high temperatures and lower times than the enzymatic synthesis, necessitating less energy. However, the use of freeze drying in the storage step equaled electricity expenditure for both processes. The environmental load associated to the purification step was due to the huge amount of ethanol used. Nevertheless, the use of huge amount of raw materials in the hydrolysis process induced the highest environmental load, which finally widely overcame the environmental burdens associated with energy or ethanol used. The results of this study help to identify the stages which need special effort to eco-design the production of FOS and GOS at pilot and industrial scales in the future. Further research should be focused in the reduction of the biomass used and corresponding solid waste generated during the hydrolytic production. Further developments should systematically include environmental assessment at each development stage to ensure the eco-design of the process. Thank you for your attention. Thank you to all the contributors of this work, and thank you to Europe for funding Premium Project.